And let's say now it's really a pleasure for me to introduce our next speaker. This is Professor Sandra Savaglio, and she's an Italian astrophysicist, and her research focuses on the young universe and origins of the galaxy. She graduated in Italy in 1992 at the University of Calabria, and she received there also, it's a few years later, her PhD. In 2004, she was on the cover of the magazine Time as a symbol of many European scientists moving to the United States. And after a lot of experience abroad, I mean, she worked in France as a postdoc, then she moved in the John Hopkins University, and then to the Max Planck Institute in Germany. And after 23 years of working outside, I mean abroad, sorry, she returned in Italy in of my university, and now she is a full professor in the University of Calabria. She received also many awards, including the Pythagoras Awards and other awards. And thanks again for your participation, Sandra. And the floor is yours now.
Thank you, Oreste. Thank you for the invitation, Oreste. It's not because we are friends, right?
No, absolutely, Sandra. I mean,
absolutely not.
I didn't mention, let's say that when I was studying in, let's say, our university, because you have to know that me and Sandra, let's say, came from the same place in Italy. We were looking at you like a star. I mean, yeah. So, I mean, it's not only for this.
The galaxy. I studied galaxy.
As a superhero, let's say. Yeah, okay.
Oreste, you're very kind. It's a pleasure really to be here. I'm very happy also that you made your career abroad and in an important place like Groningen. And so I wanted to show this because I never do it, but for once I do it myself because I have it in my room and it's hidden here. It's the Time cover. I'm very happy to share this with you for once. So, but Oreste asked me to talk about my science, and I don't want to be too technical or anything because Oreste told me that there is a large variety of students who do different things for living. So I want to be really clear what I say, and I want to you all fall in love with the things we have the pleasure to do in life. So if I can share the screen, and let's see if I can make it.
Did you send me already your presentation, Sandra?
I sent it to Nika. Yes, exactly.
Okay.
That works. Okay, Nika, thank you.
Okay, good.
All right, so thank you again, and congratulations for the other speakers, because I also saw Petra had an interesting presentation with all the progress in these actions to favor the presence of women in science. And I know Netherlands has a lot to do about this. I think congratulations, because it's showing that you recognize there is a big problem and you're doing things really the right way, I believe. Anyway, I also learned many things for the other speakers. So I will talk about the science that I do, but let me just show a couple of slides that are interesting on why we are so discriminated. Well, there are many reasons. Go to the next slide, you will see one of the sentences written by the most famous philosopher in the ancient history, who is, can you go next slide? I don't see the next. Are you in the next? I see the first.
Exactly, Sandra. We are stuck on the first slide, yes.
But it's not me. Am I sharing my screen?
No. Okay, now it's working. Okay,
Oh.
now it's working. So exactly.
Oh my God! I thought that you were.
Exactly. Now are
Okay.
you? I think.
I lost my presentation. Where is it now? Oh, wait. Oh, funny. Oh, okay. Sorry.
Good. Good.
We are scientists, but sometimes we get lost in something really simple. Okay, so so this is a statue of the head of Aristotle, one of the most famous philosopher in ancient history, and he himself said, "Where can I go? Oh, please." Why I cannot go to the next slide?
He lost his slide again, Sandra. Yeah.
I know.
Yeah.
Wait. Oh, okay. It worked. Okay, so Aristotle would say women are.
We are not seeing your presentation. No, sorry, Sandra. I'm not able to see the presentation. I mean, let's say is.
You gotta be kidding me.
Okay, Peter. Thank you, because Peter saying we were looking at the Nika's slides. Yes, exactly. Now, I mean, I see you and not the presentation, Sandra.
Yeah. Do you see mine now?
No, Sandra, no. Okay, let's say now I see.
Yes, sorry. So I couldn't do anything with my buttons. It's Nika. So I'm, yeah, now I can move. So in case I cannot, I will keep my microphone open so you can hear me, because you couldn't hear me last time.
Okay, Nika, thank you. Can you go to the next slide? Yes, move. I was reading. So Aristotle would say women are mutilated males. Their being females is due to the lack of power. Their femininity coincides with passivity, and they must be treated as passive beings, like objects. Compared to men, women would be impulsive, double, jealous, petulant, and shameless. So I'm taking this from an article of a few years ago from Lica Vassallo, who is a famous, known philosopher in Italy. So this is the opinion of Aristotle. And in the past and modern era, if you go next, will be another known philosopher, Arthur Schopenhauer. He would say women remain by nature inferior than males because permanently childish, manipulative, and liar. They lack intelligence and sense of justice. So, so these the most famous minds of the history have this opinion about women, that really there is no chance who can understand the power, or to help the society, to give the credits to the capabilities of women. Anyway, go back to science. I'd like to talk about explosion of stars, and this is something I study as a job, and in particular the exploding stars that are coming from the distant universe. But we'll talk about explosions of stars in the local universe, in our galaxy. This is the Milky Way. It's an image taken in a place nearby here where I live in South Italy. This place the mountains are called Sila. And this is an image on a lake, Ampollino, taken a couple of years ago, 3 years ago. So you see, like you've seen also from Amina, this is the image of the Milky Way. In the middle, if you can see the cursor of mine, you can see maybe you don't, but I mean, in the middle of the picture, there's the center of the Milky Way, which is the center of the galaxy. Can you go next? Now we see the entire sky in this Adam image, which includes a picture of the sky taken from every point in the planet. You can rebuild the entire Milky Way. So you can recognize a few things. If you can go next, Nika. So this is the Orion Constellation on the side of the Milky Way. The next is the Andromeda Galaxy, which is the giant galaxy closest to the Milky Way. And then a couple of other galaxies that are satellite galaxies that you can only see in the southern hemisphere. These are not possible to see them in the northern hemisphere. And these are the large Magellanic Cloud and the small Magellanic Cloud. They're about 10 times smaller than the Milky Way. Next. So before we can continue, I can show you some tools that you need to understand when we travel in the universe, how big the universe is and how far we can go. The speed of light is the highest speed reachable in nature, and it's almost 300,000 kilometers per second. The image of the moon takes a little more than 1 second to reach us every moment, and the sun takes 8 minutes to reach the Earth. Next, the distances are measured in light years for convenience because they are so large, the universe is so big. For instance, 1 light year is the distance that it takes the light to in a time of 1 year, and it's almost 10,000 billion kilometers. So the closest star is 4 light years away, Proxima Centauri, and is 40,000 billion kilometers from here. Now, because there is this limitation that light cannot move at infinite speed, then we have another dimension that you have to consider when we study the universe, which is the 4th dimension, which is time. Next. Now, for instance, our galaxy is a disk, and the size is 100,000 light years across. It means that anything that's living from one side of the galaxy will reach the other side of the galaxy in 100,000 years. Next. The Milky Way contains about 200 billion stars, among which the sun is one of those. Next. And Andromeda is the largest, the giant galaxy closest to the Milky Way, and it's 2.5 million light years from us. So the image of the Andromeda that you see every moment is 2.5 million years old. Now, this is an image of the constellation that I showed you before, which is the Orion Constellation. Next, we will show you better. So this constellation is very clearly visible now in winter. So if you have a clear sky at night, you can see it because it contains the brightest stars in the sky. And among these stars, there is the middle one. Next is the Orion Nebula, which is a region of the sky that is forming stars, and it's 1,500 light years from us. The next is Rigel, which is a giant star, blue, 860 light years away from us. And next is this red star, which is Betelgeuse, which is a little bit closer star. So these stars are kind of they look close one another, but the distance actually from one another is very, very different. It's just a projection effect. So the blue and the red stars are 2 giant stars, and they're both they will eventually will explode, because being so large, they cannot keep the pressure of gravity. So the star eventually will explode to fight against gravity. And the one that will explode because that they are finishing their fuel, so they are close to the final explosion. If you go next, I'll show you what I'm talking about. So this is a close image of Betelgeuse. It's one of the few stars that you can actually measure the size. The majority of the stars, they look like point sources. You cannot measure exactly how large they are. But this one is large enough and it's close enough that you can actually tell how large it is. And it looks like a bubble of gas, very red, because it's very large and expanded, and very large. And then that when stars get larger, the temperature of the surface goes down and they become red. Next, to tell you better sizes, I should make a comparison with the sun, which is this little dot that you see. Next, I show you Rigel, which has a mass which is 21 times larger than the mass of the sun, and Betelgeuse, because it's in mass a little smaller than Rigel, but in size is much bigger because it's expanding. So to show in scale with the solar system, if you click more, you will see the orbits of the Earth in scale and the orbits of Jupiter in scale. Clicking again. So it is really large. So what is going to happen when the star will not be able to keep the star together, because the pressure of the force of gravity will compress the star so much in the core that will explode. The star will actually become very, very bright. If you go again for the computer simulation, you can go back. Okay. All right, so let this explode. Don't move, don't do anything. It will explode by itself. Okay, so this is a computer simulation that is very realistic, and it shows that when the star will explode, the core will get very much compressed and will produce a lot of chemical elements that will actually enrich the universe with heavy elements, and the rest of the star will be expelled. The majority of the body of the star will be expelled at a very high speed, 10,000 kilometers per second or even larger, to the interstellar medium. So after years, the explosion of the star will look like a remnant. And if you go next, I'll show you a supernova remnant. It's very famous. The explosion was seen by the Chinese in the year 1054. And this object, now it's called the Crab Nebula. The distance is 6,500 light years from us. And the size of the bubble, the size of this thing that you see, is 30 light years across, more or less. So now, if you go inside the middle, you will see the remnant of the star itself, which is the core that has changed the the core is very much a compressed remnant of a star, but that is called a neutron star. So if you go next, you will see better if you observe the object in X-ray, which is the image in blue, and press again the key, and you will see where the core of the star is. It's a neutron star, which means a dense, very dense star with a size of 20 kilometers, the mass that is larger than the mass of the sun by 40%, and it will be rotating at a very high speed. It makes 30 rotations in 1 second. So it's a spectacular event. This is another remnant of an exploded star in the year 1006. It's called SN 1006, supernova 1006. The distance is 6,850 light years. And what you see is a little size of the nebula of this exploded star, which is gas enriched in heavy elements, which is moving away from the site where the star exploded. And it's a very beautiful image. If you go next, I'll show you another beautiful image, which is a remnant of another famous star called Supernova 1604. It's also called as Supernova Kepler, because it was discovered by the scientist Johannes Kepler in the year 1604. At that time, he was actually working with Galileo in Padua, and it was a few years before Galileo could use the instrument called telescope, invented by the Dutch some years ago. Galileo used this instrument for the first time to observe the sky a few years later in 1609. But Kepler saw this exploding star that today looks like a remnant, and it's showing this beautiful image taken with some telescopes. It's taken with an infrared telescope called Spitzer, then Hubble Space Telescope, a famous telescope, and then also with an X-ray observatory called Chandra. So this supernova was the last supernova identified clearly in the history of human life. And it was basically 4 centuries ago. So you can ask yourself, all right, so how often these stars explode in our galaxy? It is not particularly easy to find out. And what we can do is to count how many exploding stars have been observed in the past. So if you go, right, so this is a list of supernovae observed in the last 1,000 years. There are a couple of objects with the question marks because we are not totally sure. So few of them, I showed them. I showed you the Kepler, here it's Granchio's in Italian, sorry, I forgot to translate this. It's the Crab Nebula in the year 1054, then the Lupus in 1006, and this is also 1658. There's a question mark, we're not totally sure. This was actually supernova, but there is possibly some historical data that tells that this star that today we see it as a remnant was exploding in the year 1658. So in the last 1,000 years, there were 6 explosions. So you would say there are less than 1 event per century, but actually you have to make a lot of corrections because often the supernovae are not easy to detect, especially if you don't have the right instruments at the right time. So if you make these corrections, you can tell that prediction would say that the rate of explosions in our galaxy is about 3 events per century. 3 events per century. And the last one that we could tell for sure maybe happened about a century ago, maybe. So we actually like to see some events, some exploding stars in the next future. All right, so we go back to the Milky Way, and I'll show you again the satellite galaxies, because there was an event that happened recently that was detected in a satellite galaxy in the Large Magellanic Cloud that you see here. So the Large Magellanic Cloud is a galaxy, satellite to our own galaxy, that can be seen from the southern hemisphere. So if you're in Australia, in Brazil, or in Chile, you can see it. It cannot be seen from here. So this galaxy is a young galaxy. It's relatively small, also because it's interacting with the Milky Way. So it's losing stars with the interaction with the Milky Way, which is larger. So if you go next, I'll show you a detail of this galaxy. Here you see the distances. So the Large Magellanic Cloud is 163,000 light years from us. It's a beautiful young galaxy. And this site here, it's called Tarantula Nebula, which is a region of star formation. It's a region where there's a lot of hot gas, where stars are forming, and there are lots of young stars. So if you go next, this is a detail of the Tarantula Nebula observed in Australia. There was observed this galaxy, this star-forming region before a particular star exploded at the Australian Astronomical Observatory. So if you go next, you'll see with this arrow, blue arrow, indicating a blue giant star. This star was a giant star known, but it was blue. And at that time, theory would say that this star was not supposed to explode, but actually did. And in 1987, it was detected and the explosion was clearly seen. Go next. You will see the difference with an image taken at the time. Yes.
Sorry, Sandra, can I ask you if you can conclude in a couple of minutes? Sorry, I mean, for the technical problem.
Yes, I should be able to make it.
Thank you very much, Sandra. Thank you.
So this is supernova in 1987, observed in February 1987, and it was a spectacular event. Now, I'm sure you ask yourself, are we supposed to see some other events that are like this or even more energetic? Yes, if you go to the next slide. There are some explosions that happen in the universe that are very, no, wait, I'll go back to Tarantula Nebula. You know, since you asked me to stop in a couple of minutes, I will probably stop after this image. So this is a detailed image of the Tarantula Nebula. In particular, I'm focusing on the middle of the image, and it's called Star Cluster R136. This is in this region of the Tarantula Nebula. There are many massive stars that are eventually supposed to explode. 800 stars will eventually explode in this small region, which is 600 by 500 light years across. And in the very middle of this region, go next, there are some very massive stars. There are 9 stars that have a mass that is 100 or more higher than the mass of the sun, in a region that is only 3 light years across. So it's a spectacular region, and they will show you some really big explosions very soon. Now, if you can skip this middle image, well, actually, I'll go fast. The gamma ray bursts are the most massive stars that are going to explode in the universe and are particularly energetic, and they are more energetic than any other explosion like we have seen in the recent history. And these objects exist in the universe and they can be observed at very high distance. If you can skip a couple of slides, Nika, just skip this, not to give too many details. Okay. This is a gamma ray burst observed in 2001 in 21st of November. And the distance of this object was 4 billion light years. No, 6 billion light years. And the explosion occurred 4 billion light years ago. And this other object was observed in a telescope that is located in Sila, nearby my home. And the distance was even larger than the one I showed you before. If you click, I'll show you how far it was. The explosion was detected from Earth in October 2020. The distance is 16.7 billion light years away from here. And the explosion occurred almost 7 billion years ago, when the universe was about half the age of the universe today. Now, the very last slide is this one. You can ask yourself, what is the star that will actually explode in our galaxy? We cannot know for sure because stars will explode. The massive stars will explode, but we don't know exactly when. But this star is particularly impressive. It's particularly large, and the large stars are those that are exploding. They have a very short life. And this star is called Eta Carinae. The distance is 7,500 light years from here. So it might be that this could be the next gamma ray burst that we will see in the galaxy, and whether they will be dangerous, it will be dangerous for life on Earth, maybe, but maybe not. But there's a good news. This star can only be seen in the southern hemisphere, so if it will explode, we will be invested by the UV and X-ray light. Not much, but it will be, if there will be this explosion, it could have a big effect on the destruction of the ozone layer in the atmosphere, which is protecting life from UV light. Thank you, Oreste.
Thank you very much, Sandra, for your interesting talk about the cosmic explosion. Let's see, actually, I have a couple of questions, but we can also, let's say, do the discussion into the discussion session, I mean, of the events. So let's say now I'm